Have you ever just sat and watched steam rise from a coffee cup? Or maybe looked at the vast, swirling arms of a galaxy in a picture? Well, our whole universe is in constant motion. It's this grand, unseen dance, and it's all choreographed by the laws of fluid mechanics. And today, we're going to pull back the curtain on this amazing world, one core idea at a time.
And what's really incredible is that the exact same physical laws that describe water flowing in a stream are the ones that describe the rotation of an entire galaxy. That's not a coincidence, you know. It's a huge clue that points to a deep, universal truth about how everything works.
I mean, think about it. We are literally surrounded by fluids in motion all the time. The air we breathe, the water we drink, the clouds in the sky. Their movements can look so beautiful, but also incredibly complex, almost chaotic. The whole point of fluid mechanics is to find the simple, elegant order that's hiding inside all that chaos.
So this is the big question, right? How do we even start to describe this beautiful mess with math and physics? Well, the secret isn't to look harder, it's to look smarter. We just have to choose the right point of view.
Okay, so the very first step to understanding all this complex motion is deciding how we're going to look at it. And it turns out, in fluid mechanics, there are two totally different but really powerful ways to see the world. So the first way is the one that probably makes the most sense right away. We call it the Lagrangian view. Just imagine following one single drop of water on its whole journey down a river. Simple to picture, right? But it's basically impossible to track every single drop. So physicists use a much more powerful method, the Eulerian view. Instead of following the drops, we just plant ourselves at one spot and measure the properties of whatever flows past us. Its speed, its pressure, you name it. This one brilliant shift in perspective is what makes all that chaos manageable.
But hold on, before we can even measure a fluid that's moving, we need to understand what it even is at a basic level. What makes a fluid a fluid? What are its core properties when it's just sitting there, perfectly still?
You know, every fluid has its own personality, and it's defined by three main things. First, you've got density. That's just how much stuff is packed into a certain space. Then there's pressure, the constant push it exerts on everything it touches. And finally, there's viscosity. That's basically its stickiness or its resistance to flowing. It's the difference between water and honey. That gooey resistance, that's viscosity.
So let's start with the easy stuff. In a fluid that isn't moving, what we call fluid statics, everything's pretty calm. The only real force you have to worry about is pressure, and it always pushes straight out at a perfect right angle to any surface it touches. This super simple rule is the foundation for everything else.
But let's be real, fluids rarely just sit still. So now that we have the rules for stillness, let's get things moving. We are now officially entering the world of fluid dynamics, and this is where the real action starts.
I want you to imagine we could zoom way in on one tiny little parcel of water in a river. It's not just floating along, oh no. It's being stretched and squeezed and spun around by all its neighbors. And every single little movement is a direct response to the forces that are being put on it.
To describe all of this pushing and pulling, physicists use one of the most important equations in all of science, the Navier-Stokes equation. Now, it can look really intimidating, but the idea at its heart is actually super simple. It's just Newton's second law, force equals mass times acceleration, but rewritten for fluids. It's the master rule that connects all the forces to how the fluid actually moves.
So, what are these forces? Well, the equation is really just this elegant balancing act, a constant push and pull. On one side, you have inertia. That's the fluid's stubborn tendency to just keep doing what it's already doing. And then pushing against it, you've got three other main forces: the squeeze from pressure, the drag from its own internal stickiness or viscosity, and of course, the downward pull of gravity. And that's pretty much it. The entire dance of fluid motion is just a constant negotiation between these four players.
Okay, so we've got this master equation. That's great, but how do we actually use it to predict what the flow is going to look like? How do we know if it will be smooth and orderly or totally wild and chaotic? How do we crack the code for chaos?
Well, the key is this really powerful little tool called the Reynolds number. It's just a single number, a simple ratio, that compares the strength of a fluid's inertia, its tendency to keep moving wildly, against the strength of its viscosity, that internal friction that's trying to calm everything down. This one number tells you the whole story.
So when the Reynolds number is low, it means viscosity wins the fight. The internal friction is strong enough to keep all the fluid particles moving in these smooth, neat, parallel layers. Think of thick honey slowly oozing down a plate. That really orderly state? That's called laminar flow.
But when the Reynolds number gets high, inertia totally takes over. The fluid's own momentum just overwhelms its internal stickiness. It breaks free into this chaotic, swirling, unpredictable state that's full of eddies and whirlpools. This is the turbulence you see in a crashing waterfall or a raging fire.
Okay, so we have our viewpoints, we have our core properties, and we even have a tool to predict chaos. Now for the really mind-blowing part. Let's see just how powerful these ideas are. This is where we find out that these few simple principles apply across almost every field of science, on every single scale you can possibly imagine.
I mean, the scope here is just stunning. These exact same rules are used to design supersonic jet engines, to model our planet's weather systems, and even to understand how tiny bacteria manage the fluidity of their own cell membranes. And then on the largest scale, cosmologists model the expansion of the entire universe as if it were a perfect fluid. And on the smallest scales, even bizarre quantum systems can be described with these very same equations. It's wild.
And this right here is the ultimate takeaway. This is the real aha moment. These simple, deep ideas about conserving mass and momentum, the very principles at the heart of the Navier-Stokes equation, they're like a golden thread, connecting the most practical engineering problems to the most abstract questions we have about the universe itself.
So the next time you see smoke curling from a chimney, or a river flowing, or just clouds drifting across the sky, you're going to see it differently. You'll see that battle between inertia and viscosity. You'll see those universal laws playing out right in front of you. You know the rules of the unseen dance now. So the only question left is, what are you going to see?